In this lesson we're going to look at an application of integration or antidifferentiation, which is to find the area under a curve. Now by this we mean the area between the curve and the x-axis, and it's usually bounded by some x values. So in this case we've got the curve y equals x squared, the x-axis, and the x values 0 and 1, and these define this shaded area. An estimate for the area can be found by splitting it into rectangles. In this case I have divided the area into 10 rectangles, so the width of each of these rectangles is 0.1. And I've done this twice, once for an overestimate and then for an underestimate. So you see with the overestimate the heights of the rectangles are above the curve, and with the underestimate the rectangles fit just below the curve. Now to work out the area of each of these rectangles I need to multiply the width 0.1 by the height, and to work out the height of each rectangle I can use the equation of the curve. So with my overestimate, the first rectangle has a height of 0.1 squared, and the second rectangle has a height of 0.2 squared, and so on up until the tallest rectangle, which has a height of 1 squared. And in the underestimate, the smallest rectangle is where this gap is here. That's 0 squared. And then the second rectangle is 0.1 squared, up to the highest rectangle for the underestimate is 0.9 squared. And then in each case we add the areas of the rectangles together. So notice that we're actually using the same rectangles. The overestimate has a rectangle with a height of 0.9 squared, but it also has this additional rectangle with a height of 1 squared. I've set this up on a spreadsheet, so I have the values from 0 to 1 going up in 0.1, and I've squared each of these values to find the heights of all the rectangles. Now the overestimate includes all of these values apart from 0, and the underestimate includes all of these values apart from 0.1. Once I've got the overestimate and the underestimate, I average out these values, giving me an approximate area of 0.335 square units. We can improve on this model by making the rectangles narrower and increasing the number of rectangles. You can try this yourself if you set up a spreadsheet like the one I just showed you, but divide the area into 20 rectangles or 50 rectangles or 100 rectangles and see if you can improve on that estimate for the area. Now if we make the rectangles as narrow as possible and we define the width of each rectangle as delta x, and then the height of each rectangle is found using f of x, we can say that the area under this curve y equals f of x from x equals a to x equals b is given by the limit as delta x approaches 0 of the sum from x equals a to x equals b of all of those f of x values multiplied by delta x. And for this we use an integral symbol. We say that we're integrating from a to b f of x with respect to x. So just as differentiation dy by dx can be defined in terms of gradient, the integral can be defined in terms of area, and it's the limit of the sum of the area of all of these rectangles as the width of the rectangles approaches 0. This is known as definite integration, and you can recognise definite integration because of the numbers at the top and bottom of the integral symbol. So what we're saying here is we're integrating from a to b a function with respect to x, and that means that we want the antiderivative of that function, and we're substituting in the values of b and a and subtracting. We'll demonstrate using a linear function because we can work this area out without doing any calculus. We've got the line y equals 2x plus 3 and x values of 1 and 3, and the x-axis is our boundaries. This is a trapezium shape, so to find the area of a trapezium, it's a half the sum of the lengths of the parallel sides, so 5 plus 9, multiplied by the height of the trapezium, so that's 2, so 14 square units. Or I could divide it into a rectangle and a triangle. This is 2 by 5, which is 10, and then this is 2 by 4, half of that is 4. Using integration, I would say that this is the integral from 1 to 3 of 2x plus 3 with respect to x. So I need to anti-differentiate this expression. The antiderivative of 2x is x squared, and the antiderivative of 3 is 3x. And I write this in square brackets with a superscript 3 and a subscript 1 to show that I'm going to substitute in these values and subtract. So we've got 3 squared plus 9, take 1 squared plus 3, which is 18, take 4, 14 square units. Now make sure that you follow this, and especially make a note of the notation here with the square brackets, where to put the numbers, which values are substituted, etc. In this example, we're looking at the area bounded by the curve y equals x cubed, the lines x equals 1, x equals 2, and the x-axis. We could estimate this area by dividing it into sections. This is 1 square unit, and I could say this is almost another square unit. If I put that together, there's 2 square units altogether. Looks like it's going to be just over 3 square units. But we'll work it out using definite integration. To integrate x cubed, it's x to the power of 4 over 4, square brackets, and I'm going to substitute in the values of 2 and 1. So this is 2 to the power of 4 over 4, take 1 to the power of 4 over 4, which is 3 3/4 square units. Now you might be wondering what's happened to the plus c. If I go back to this step and this time include the plus c, so this would be x to the power of 4 over 4 plus c. Remember that c is a constant, so when I substitute in, I'm going to have 2 to the power of 4 over 4 plus c, take 1 to the power of 4 over 4 plus c. Now don't forget this is in brackets because I'm subtracting this whole term. And you can see now that these plus c's are going to cancel and leave me with 2 to the power of 4 over 4, take 1 to the power of 4 over 4 as before. So it wouldn't be incorrect necessarily to write the plus c here, but it's just not needed. I'm going to work through a few examples, and as always you should pause the video and try these on your own before watching my solutions. These first two examples are indefinite integrals. There's no numbers on the integral symbol. Raise the power by 1, divide by the new power, and don't forget the plus c. In this second one, I'm going to write it in index form first. So this is the integral of x to the power of a half with respect to x. Raise the power by 1, divide by the new power, and don't forget the plus c. And it's always nice if the question is given in surd form that your answer is also written in simplified surd form. These next examples are definite integrals, where we do have the numbers on the integral symbol. X cubed, 4x, square brackets, 2 and 1. So we've got to substitute in these values. 2 cubed plus 8, take 1 cubed plus 4 is 11. Now this isn't an area question, it's just saying find the definite integral. So I don't need to write units squared here. You only need to write units squared if the context is an area question. This final example is a product, but there's no such thing as a product rule or a quotient rule in integration, only in differentiation. What we do have and what we need to check is, can we use the reverse chain rule? The derivative of what's in the brackets is 3x squared, so I know that the integral of 3x squared x cubed plus 1 to the power of 4 is x cubed plus 1 to the power of 5 over 5 plus c. But I've actually got 6x squared, so I need to double this and hence double the result. So going back to my question over here, this is going to go in square brackets now because it's definite integration. 2x cubed plus 1 to the power of 5 over 5. I don't need the plus c, and I need to substitute in the values of 1 and 0, which is 62 over 5.